This is the second short lecture of Chapter 35, dealing with geometric optics, and we're going to focus on refraction. When a ray of light traveling through a transparent medium encounters a boundary leading into another transparent medium, part of the ray is reflected, and part of the ray enters the second medium. We say that this second ray that enters the second medium and is bent at the boundary, we say it is refracted. And the bending of the ray is the process of refraction. It can look something like this. We have an incident ray coming in, and we have a reflected ray and a refracted ray. The blue is the reflected ray, and the refracted ray is theta 2. If we're going from a lower speed index to a higher index, then it's going to be refracted towards the normal. So the properties of the refraction are going to depend on the medium it goes into. Here's an example of rays. We have an incident ray, ray 1, coming into this lucite, and part of that ray is reflected as ray number 2, and part of it is refracted into the lucite and bent towards, inward. Then we have ray 4 that's internally reflected off the other edge of the lucite, and then as it's coming back up, it is refracted away as ray number 5. And we'll learn later, if we do some geometric analysis of this, we can see that ray 2 and ray 5 are actually parallel as they come out. Well, we can think of refraction as these wavefronts coming in, and the speed of the rays coming in, the speed of the light coming in, going from a higher to a lower speed. And in that sense, it's going to refract towards the normal. The normal, again, is that line that is perpendicular to the surface in question. Light may reflect into a material where its speed is lower. The angle of refraction is less than the angle of incidence. So in this case, theta 2 is our angle of refraction inside the second medium. Theta 1 was our angle of incidence, just like what we had with reflection. And we can see that theta 2 is less than theta 1 because we're going from a material where the speed is faster to a material where the speed of the light is slower. So the ray bends toward the normal. Here's kind of an example, mechanical example of what's going on here. If we think of this barrel as a wavefront, and the direction this barrel is moving as the ray, as it's moving across some concrete, it can move pretty fast in one direction in the concrete, but when it hits the grass, one end of the barrel will start moving slower as it hits the grass, and that will cause the barrel to start turning. Hence, when it finally enters the grass, it'll be moving in a different direction. If the grass is uniform, it'll continue to move in a straight line after that direction. So there'll be a bend that occurs at the interface between the concrete and the grass based on the fact that the barrel moves slower in the grass than it does on the concrete. We could also go from a medium where light is traveling slower to a medium where it's traveling faster, and in this case it will refract away from the normal so that the angle of refraction will be greater than the angle of incidence. In this case, the ray bending away from the normal being that perpendicular line to the interface between the two medium. And we could use a barrel example again. If the barrel were rolling in grass where it's moving relatively slow, it'll move along some straight line and have some ray associated with that. But as it starts to go, as one end of it gets into the concrete, it'll start moving faster, and the barrel will turn. And then when all of it gets into the concrete, will continue along a straight line after that. So there will be a bending that occurs at the interface between the grass and the concrete, going from slow to faster, and it will bend and move away from the normal. Light is refracted because the speed of light is different in these two media. Light's traveling through, say, air or even a vacuum, and it travels in the glass and moves slower in the glass than it does in air. And it's not because light itself is moving slower, but it's because the interaction of the medium is making it, on the whole, move slower through that medium. So the speed of light in air is 3 times 10 to the 8 meters per second. In glass, it's 2 times 10 to the 8 meters per second. And the air is 3 times 10 to the 8 meters per second again. So it moves about 2/3 the speed in glass. The reason is light excites electrons within the medium, in this case glass. The electrons oscillate and they re-radiate the light. And this process takes a little bit of time. So light actually will travel from atom to atom at its designated speed of 3 times 10 to the 8 meters per second. But the fact that it's being absorbed and re-radiated through this medium means that its ultimate speed through the medium is going to be somewhat less. And so if we measure the light through the medium, it's 2 times 10 to the 8 meters per second, even though the light itself, as it's traveling from point to point, is still moving at 3 times 10 to the 8 meters per second. We define the index of refraction of a medium as being equal to the speed of light in a vacuum, which is its fastest speed, designated by c, 3 times 10 to the 8 meters per second, divided by the speed of the light in the medium itself, which will be somewhat less than the speed in a vacuum. So for a vacuum, the index of refraction is 1, because you'd have c over c. But for other medium, the speed of light in any particular medium is going to be less than its speed in a vacuum. So this fraction is going to be greater than 1. It's going to be dominated. It's going to dominate 1, so it's going to be greater than 1. So there won't be any indices of refraction that are less than 1. And as a unitless ratio, it's just simply the ratio of these two speeds. Speed of light in a vacuum to the speed of light in the medium, and it's going to be a number greater than 1. Here are some indices of refraction. The largest one we can see is diamond, pure carbon in a nice organized form. Has an index of refraction of 2.419. And we look at glass. Generally, we're going to treat glass as being about 1.5. Different kinds of glass. Sodium chloride as well, about 1.5. We get to zircon, 1.9. So that's not too bad. If you had something made out of cubic zirconia, it would have a lot of reflections and refractions and get a lot of brilliance out of that, but not quite as good as a diamond. A diamond has a high index of refraction, so you can get a lot of internal reflections in a diamond, and hence it's going to make it appear much more brilliant. So you can actually tell between a cubic zirconia and a diamond which one is indeed the diamond, based on its brilliance. When we're treating light and its interface with different media, the frequency does not change as it enters into another media. It is the wavelength that changes. If you're going from where the speed is faster to where the speed is slower, the reason it's slower in the new medium, or one reason as far as a mathematical sense, is that its wavelength between wavefronts is shorter, but the frequency doesn't change. So as light travels from one medium to another, frequency doesn't change. Both the wave speed and the wavelength change proportionally. The wavefronts don't pile up at the interface, nor are they created or destroyed at the boundary. So this allows continuity of the light as it goes through the interface, and it also allows continuity of the photons in a sense, because photons relate to the frequency. So the wavefronts do not pile up in the interface. The frequency stays the same. The ratio of the indices of refraction of two media can be expressed in various ratios. We have it as the velocity 1 going to velocity 2 is index 2 over index 1. And the same thing as the wavelength 1 to wavelength 2 is the same as the velocity 1 to velocity 2. That's equal to the speed of light over index 1, speed of light over index 2. Speed of lights cancel out, and that's what reverses our ratio of indices. So here's a useful formula you can use just for the ratio of speeds, the ratio of wavelengths between two media. This brings us to Snell's law of refraction. And it goes like this. Index 1, sine theta 1, which would be the sine of our incident angle, is equal to index 2, sine theta 2, where theta 2 is the angle of our refracted ray. So this is Snell's law and applies between an interface between two media for light. Theta 1 is the angle of incidence, 30 degrees in this diagram. And theta 2 is the angle of refraction. A very useful law, Snell's law of refraction. Turns out that the index of refraction depends on the wavelength just a little bit. And here's a chart showing not much variation in the index as we go through visible light from 400 nanometers to 700 nanometers. This slight change in the index of refraction is called dispersion. N will usually decrease with increasing wavelength, or in other words, N will decrease with decreasing frequency. N will go as your frequency. So the higher the frequency, the higher index of refraction. The lower the frequency, the lower your index of refraction. It decreases with increasing wavelength. Violet light will refract more than red light when passing through a material. So here's a prism, and the violet light will refract more, here looking like blue, hence it's going to bend more, and the red light will refract less and bend less. In essence, the velocity of red light is faster in this medium than the velocity of violet light. So the speed of red waves is faster than the speed of blue waves, giving red waves a longer wavelength and bending less than the blue with the shorter wavelengths. So blue is bent more, giving us the full colors of the spectrum out of the white light. Here's refraction in a prism. We actually have two refractions going on in this particular prism. And the amount the ray is bent from its original direction with these two refractions is called the angle of deviation. So if I have white light coming in, red is going to refract into the medium and then refract out of the medium. Same thing with blue light, but ultimately blue is going to be deviated more than the red light. And so we're going to have two different angles of deviation for red as opposed to blue. Since all the colors have different angles of deviation, they'll spread out into a spectrum, and the prism will divide the white light into the spectrum of colors. Violet would deviate the most, red would deviate the least. What about the rainbow? What happens with the rainbow? Usually you have a source of light, the sun, behind you, and you're looking out where maybe a storm has just passed through, and there's a lot of pretty well consistent water droplets in the air, all about the same size in front of you. And as the light comes into those water droplets, it's going to refract and deviate according to the different indices of refraction for the colors. Then will internally reflect inside the water droplet, come back and refract again, giving you an angle of deviation between the incident light and the out light, and hence splitting up the light into the colors. So a ray of light strikes the drop of water, is refracted, then internally reflected, then refracted back again, and that light comes back towards you, and you see the different colors. The angle between the white light and the violet ray is 40 degrees. The angle between the white light and the red ray is 42 degrees. The angle has to be just right with the setting sun or the angle of the sun to get this effect to happen. And that kind of difference in degrees is what you see as the rainbow. So here's a fellow observing the rainbow. The raindrop high in the sky is observed, the red ray is seen, and maybe the violet ray is above your head at that point, from that point on the rainbow. A drop lower in the sky would direct violet light to the observer, and then you don't see the red light because you're just looking at the angle where the violet light comes in. If you lowered your eyes, then you would see the red light. The other colors of the spectrum lie in between, and hence what you see at that moment is the colors of the rainbow. Here's an example, a nice situation of farm setting, and we have ourselves a rainbow. It's hitting this farm. Something is missing in this picture, because every time you see a rainbow, there should be a pot of gold at the end of the rainbow. And we have another rainbow. We have a secondary rainbow. Yep, there's a pot of gold there. So, good. All right, so everything's in order here. Notice you have your primary rainbow with all the spectrum of the rainbow and all the spectrum of the colors from violet to red. And then you have your secondary rainbow, and the colors are reversed. And they're kind of more diffuse too, so not as well-defined rainbow. Why is that? That's a good question. Well, if you're looking at a rainbow, you're going to actually see two examples of reflection and refraction. The primary rainbow is just as we described. You have refraction, reflection, refraction coming back to you. You see the primary rainbow. A secondary rainbow will have two internal reflections. So you have a refraction that comes in, reflects, and then reflects off the same water droplet. Two internal reflections, which has the action of reversing the order of colors as you see it, as it refracts again towards you. That's why the secondary rainbow is actually reversed in the order of its colors. Here's another great picture of a primary rainbow, and you can see the secondary rainbow behind this person. Excellent picture. Actually, the secondary rainbow, which actually looks like it's further off in the distance, is actually closer into you. Those water droplets are actually closer into you, but that secondary reflection is less prevalent, less probability of that light getting to your eye. Hence, it looks more diffuse and looks less defined than the primary rainbow, but actually it's closer in to you than it's not really further away. You can also have total internal reflection. This occurs when light moves from a medium with a higher index to a medium with a lower index. And so you have light that's reflected and also light that was being refracted more and more away from the normal. If you get to the point where the refraction of the light would have been 9 degrees, then none of it's going to be refracted and all of it's going to be totally internally reflected. So that will occur at the critical angle. A particular angle of incidence will result in an angle of refraction of 9 degrees. If we use Snell's law for this, we would just have a sine of 9 degrees for angle of for the part of the refracted angle, and sine of 9 degrees is 1. So this critical angle will occur when the sine theta critical is equal to index 2 over index 1. In other words, normally we have our angle of incidence from the higher index of refraction to the lower, and our angle of incidence is our critical angle. Our angle of refraction is 9 degrees. And using Snell's law, we come up with this expression for the critical angle. Sine critical is n2 over n1. Remember, n2 is less than n1, so we can get a sine of this angle that is less than 1. Take the inverse sine of that, and you'll get the value of that angle. This kind of principle of total internal reflection is very useful for fiber optics. Plastic or glass rods are used to pipe light from one place to another. Hence, you can actually have a bending of these pipes and move the light around because it's just totally internally reflecting all the way around. And hence, you can actually manipulate this light and use it in different directions. Applications use medical use of fiber optics to look and diagnose correction of medical problems. If you're trying to repair a knee and the doctor's trying to look at your knee, then you use fiber optics so you can get that image as you're looking to do orthoscopic surgery. Telecommunications use this so you can use the speed of light to help transmit information from one place to another. Just saw that a nice pattern of graphene can allow electrons to travel in a similar way to fiber optics, hence speeding up electric signals as well, and that will lead to even faster computers. So what a great idea. Here's light passing through a slab. We know that light coming in from a lower index, say to the index of the slab, will obey Snell's law. And so index 1 sine theta 1 will equal index 2 sine theta 2 according to Snell's law. As that light passes through the slab, it encounters another interface back to the original medium, and we know Snell's law should apply to that interface as well. So n2 sine theta 2 should equal n3 sine theta 3. If n1 and n3 are the same index, we can cancel those out, and we should see here from two applications and combining these Snell's law that sine theta 1 should equal sine theta 3. In other words, theta 1 will equal theta 3. So the original ray will come, get deviated a little bit off track by distance d. Theta 3 will have the same outgoing angle, and so our outgoing ray will be parallel to our incoming ray. It just will be deviated at some certain distance caused by the refraction through the slab. That could be useful. I'm going to finish up with the rainbow there. And that concludes our second short lecture of Chapter 35, Geometric Optics. Enjoy.